Okay, today we are going to see the concept of a transfer function, and I just wrote down on the right hand side over here what the transfer function fundamental concept is. It's the relationship between an input and an output. So why don't we define on the left hand side over here what my inputs are? What is my input over here? So this is my input, in this case voltage of time, a function of time obviously, and I am going to define as an output, we can have the voltage C. Also we could say the voltage of the inductor. These are the outputs. Okay. So how do we establish this relationship between the input and the output? We start by writing the equations of the system. A lot of things that we do in this class require that. This is no exception. So in this particular case, let's just go over here and say, if you write Kirchhoff's law, you know that the summation of the voltages around the loop adds to the voltage V. So we could say that the voltage of the resistor plus the voltage of the capacitor plus the voltage of the inductor should be equal to the voltage V, right? Now, in this case, so this is the basic equation, right? So what is the voltage of the capacitor? Isn't it true that voltage of the resistor in this case would be I times R, right? What about the voltage of the capacitor? Is 1 over C times the integral of I dt, right? That's what this is. And what's the voltage on the inductor over here? Voltage of the inductor is I or L, I guess in this case. We usually use the value L, this is the value C, this is the value R. Yeah. So this would be L times di dt, right? This is equal to V. Yeah. So this is basically our system equation. But in here, this is in a funny way, because it has the integral here, it has derivative over here. We don't want it in that form. Let's consider that I is like dq dt, where q is in this particularly the charge, yeah? So and here you will have R is going to be, R times, just do it right. So this would be I times R, which would be, in this case, R times dq dt like that, plus 1 over C. If I is dq dt, the integral of I, so if you integrate both sides, like, let me just put it over here, because I want to keep the right hand side free, so we can write over here. The integral of I is q, so this is going to be the integral of I is C. You see, if you integrate both of the sides, the integral of I is really q. And then plus L I would be this would be d square q dt square. Yeah? Is everybody with me? And now we have the equations of the circuit in normal form and with differential equation in there, and where the variable q, the charge, is the main variable here, the unknown. So I think that what we need to do is to establish a relationship between the voltage C and the input. So in other words, we want the relationship between voltage C and also the relationship between the voltage I, like this. This is the so-called transfer function. Okay, so it follows that if you have this relationship, think about this. If you have, let's put it this way, B of C divided by B, this is the transfer function like that. Consequently, isn't it true that the output C could be the transfer function multiplied by B, right? This is why control engineers use this, because you can find out an output by knowing the transfer function and the input. The same thing is true if you know this relationship. Let's call it the transfer function 1, and let's call this transfer function 2. So consequently, the voltage of I is got to be transfer function 2 multiplied by B. You see, this is where we're going. The question is how we get there. So a relationship between the input and the output. So what we did as number 2, we said derived the differential equations of the system. Yeah. And then as number 3, we need to apply the Laplace transform. Now, how in the world does that work? Okay, what is it to begin with? Okay, in this particular case, we could reorganize this from the highest derivative to the lowest, just to be more organized, but we don't really have to. The point here that we need to do is the Laplace operator is defined like this. The derivative of any variable time is the operator S. This is called the Laplace operator. Laplace was a professor at the University of La Sorbonne in Paris, and discovered this a very interesting and very useful method of converting differential equations into algebraic equations using this transformation called the Laplace transform. So if d dt is S, it follows that d squared dt, in this case, if you put it like maybe the variable x, s times x of s, like this. But let's leave it alone in here. I don't want to sort of tamper with the concept of it, so I don't mind writing it again. This is, the basic concept is like this, that d dt is the Laplace operator. So if we have dx dt, it follows that this is s times x in the domain S. See? If you have d squared of x, again, let's do it the same way, because it doesn't cost us any more, but on the other hand, it might make it very clear for somebody. Dx squared, dt squared of any function, this is s squared. So you can say, consequently, if you have dx squared of x, dt squared, this is s squared times x of s. Having done this, we apply this Laplace transformation to this equation. So what I would do is, I'll apply the Laplace transformation to this. So why don't we just put in the in here as a title, I will say apply the Laplace transform. So in this particular case, we say, okay, this is R times what you see dq dt is this case, times S times q of s, right? That's for this. This other one plus 1 over c times q of s like this, plus L times s squared times q of s like this. This is equal to the voltage in the S domain. Okay, so what we need to do now is, let's take this variable q out, and we can write that this is L times s squared plus R times s plus 1 over c times q of s equals to v of s. And you see the relationship. This is a, in this case, is a state variable. So you have the relationship this between this. You could define that the relationship q of s with regards to the input of s like this. Now let's just put it in the form that we can clearly see our transformation. So in here you have that q of s is equal to 1 over L s squared plus Rs plus 1 over c times what? V of s. This thing that you see in here, this fraction that you see right here, this ratio, this is your transfer function. So it follows that this output is the transfer function times the input. But you see, this was our objective. But, you know, we want the voltage C divided by V is equal to the transfer function 1. This is what we don't have. This is what we would like. Now remember what the voltage C is. B sub C was 1 over C times the integral of I dt, right? Or we said that this was 1 over C times Q, right? So if this is true, you see what's happening here? Voltage C is equal to 1 over C, but Q we have here. See, we have here. Times 1 over L s squared plus R s plus 1 over C. And this would be multiplied by B of s. So, consequently, the voltage C divided by the input in here is going to be, you could bring that C in, L times C times S squared plus RC times S plus 1, right? And this is in here, of course, is the transfer function. What about the other one? Let me just also write it in here. We also want voltage I divided by V equals, transfer function 2. So in this case, you have that the voltage of I, voltage at I is what we want. This was L times di dt, or this was L times d squared q dt squared, which, you can express it in the, this is B of I, So you could say that this is B of I S is equal to L times S squared. This is times Q of S, based on what we did up here. So if this is true, you see you have Q of S in here. Voltage I of S is going to be equal to L times S squared times this Q of S is 1 over Ls squared plus Rs plus 1 over C, and then times V of S. So if this is true, you could write that V of I of S over V of S is a numerator that's Ls squared divided by Ls squared plus Rs plus 1 over C. Of course, you could bring this down and have it in a different way, but those are the two expressions we were looking for. You see the transfer function first to the voltage C in here, and then the transfer function for the voltage on the inductor over here. So that the one up here is transfer function TF1. In this way, this is the transfer function TF2. So now this is as you do it by hand, but I told you that you could actually use CAMG to get this. Let's just apply the Laplace transform, and then you could say determine the relation between the state variables and the input, and then 5 I would say relate the output given to the input based on the transfer functions found for the state variables. And then here as you find the relation between the output and the input desired. That's how you obtain the transfer function. So this is the way you obtain a transfer function. If you have this, it's very obvious that the transfer function, the voltage C would be the transfer function times the input. Same thing over here, both. So this is how we basically obtain the transfer function.